Good morning, students. It will get warmer towards the end of the week. At least that's what the forecast is. Um, I think I've mentioned many times that we're in this strange weather pattern, and we get more rain than we'd like, and we feel the cold because of the humidity. But keep warm and drink plenty of fluids. That's always a good way to make sure you stay healthy during finals week and things of that nature, especially when tension and anxiety is a little bit higher. You just got a lot of things to do, and it's unfortunate that the end of the uh, fall semester, coincides with our holiday season. It just makes it more busy, and I think the older you get, the less fun you have during the holiday season. So remember the times when you were 3 and 4 years old, when the holiday season was fun because you didn't have as many obligations. I often think about the times growing up in North Carolina, when Christmas was a magical time, or the holiday season that you may be celebrating, whatever that may be. So what I want to do today, your final exam is posted, and I want to go over some of the examples from the practice test that I posted. And if I have some time, I've promised to say a little bit about rotation of axes. If I have time to say a little bit about it, I will. It just depends on how the time flows as we go through these practice exercises. But I've said many times, uh, review the new. Again, there's not going to be an overemphasis on the new material. Everything's going to be spread out nice and evenly. So you don't have to expect 50% on new material. It'll be, like I say, there'll be examples from each topic, uh, more survey-like. So again, don't worry that there's just going to be this overabundance of new material. Everything is spread out nice and evenly, just like I said. So, as you review, go over the new, but then also review the older material where you think you may just need some repair work, so to speak. If you're just rusty, go over a quiz, go over an old test, look at some of the old videos, the SmartPen videos or the YouTube videos that I post from our class. Again, you know yourself the best. And I guess also with the examples that we go over, that'll kind of help you realize where you need to do any review. But I think if you put in the time, which is certainly the case for pretty much everybody in the class, you'll find that the final exam is very straightforward and basically testing you on the fundamental ideas that you need to have success in calculus. So let me go ahead and share my screen. And I had the IPEVO up, and then of course it crashed again. I don't know what's up with that. Let me revive it. Sometimes it just has a mind of its own, kind of like Professor Ron, right? I can't. I'm happy for my document cam, but sometimes it does some quirky things. So there we go. And let me close this and reopen it. There we go. Okay. Now, what I want to do, I've written up, of course, all of these solutions are on the SmartPen videos, but I wanted to go ahead and give you just a hard copy of the solutions so that you have two ways to access them. So you've got the actual test copy, and then you have the written solutions, and then you have SmartPen video with Professor Ron. So it's all good. So what I wanted to do is basically go through my solutions here and point out some important concepts that we need to remember. So as you can see, most of these problems are very standard. It starts out just like college algebra, and then we make our way into the trig, and then a little bit with the conic sections and just the new material. So very, very, very standard. Now, the first example is to find a domain. That is, we have h of x is equal to x minus 3 divided by x cubed minus 81x. And what I've done is I've worked all of these examples out, and I just want to go through them. Some are very simple, so don't yawn too much if you find them very easy. Now, first, when we think about domains, we're always interested in real valued functions of a real variable. So again, we don't want to take even nth roots of negative numbers, and we don't want to divide by zero. So the best way to attack this is to think, okay, well, there are no radicals here, so let's look at the denominator and see if it can actually be zero. Well, notice we have a common factor of x, and that leaves behind an x squared minus 81, which again is a difference of two squares, very straightforward. And of course, we need this to be non-zero, just like doing the domain of a composition. And just remember, I can't test you on every type of problem that you found on the old test. So that's why the final exam is kind of like the most simple test you take out of the whole term. So again, don't fret about it. Just know that if you've done the hard work, you've already basically prepared for it. So now, of course, by the zero product, that would mean x is not equal to 0, x is not equal to 9, and x is not equal to negative 9. So you can actually state this as you saw on the answer choices, where x is not equal to these three numbers, or just to practice with the interval notation that you see often on WebAssign, you would basically have negative infinity to negative 9, and then of course union negative 9 to 0, just omitting all of these numbers, then 0 to 9, omit the 9, and then 9 to infinity. So again, just like you've always done in the past, be sure to follow formatting, just as you've done on quizzes, homework, tests. No changes, no changes. Now, the next example, again, is something that you will do often in the calculus, and the notation will often change. Sometimes the h will be replaced with the symbol delta x, just because that's a common notation for a non-zero real number, like delta x could be 1/2, or delta x could be negative 1/8 or something like that. But the delta x is just one number. It's not a delta times an x. It's just one symbol, two symbols that creates one real number. So some students don't particularly like that, but unfortunately it's very popular. The differential notation you will use in the calculus, which you will find to be very, very useful. And that's attributed to Leibniz. So here we have f of x plus h minus f of x divided by h. Again, this is a difference quotient, which you will use to make a definition for a derivative of a real valued function. And of course, h is non-zero. So we're asked to do this for this particular function. Now, when you look at this, again, this is a very straightforward calculation. What you can see here is the f of x is 1/9x, so we want to create the difference quotient. So what I do first, which I've done before, often when we're doing calculations, it's better just to kind of remove to the left something in the denominator that's really not having much interference with the work being done here. So you can just pull this over to the side as 1/h. Like that were a 2, that'd be just a 1/2 that's hanging out. Now, of course, we have f of x plus h. That is, we replace x with x plus h, and that gives us a 9 times that quantity, or 9x plus 9h. And then, of course, f of x is just as it's written, 1/9x. Now, of course, there's nothing wrong with this. And of course, if you were to type this into a WebAssign problem or whatever, it would check it as being correct. But when you're doing the calculus, obviously, in order to be able to compute a limit, you need to know that the h will somehow absorb and that you end up with a function with a hole in it. That is, that the numerator gets actually converges to 0 faster than h. And that's again the arithmetic of calculus. So how do we figure that out? Well, we just do basic algebra. Let's just get a common denominator, as we've done countless times in this course. So we have a 9x plus 9h times a 9x. And then, of course, here we have to repair a little bit. when we look over here, we don't have the 9x in this denominator, so we've got the 9x. And over here, of course, we don't have the factor 9x plus 9h. So we multiply the -1 by those two quantities, and we get a -9x and a -9h. And then, of course, you see that the 9x terms absorb, and you're left with a -9h. The 1 over h is outside, and then the 9x times the 9x plus 9h. Now, of course, this is really the goal here. This is actually going to tell us that the limit exists as h approaches 0. Notice the h is absorbed, and also the 9 and the 9 here absorb, leaving us with a -1 over x times 9x plus 9h. And if you want, you can factor the 9 if you want. Either one of these are fine. And so you get a simplified difference quotient. So now what you can see as h tends to 0 or converges to 0, this particular quotient converges to -1 over 9x squared. And so, ladies and gentlemen, that will be a way of actually determining the derivative relative to x of this function. But of course, as you take the calculus, you will find theorems that will be a little bit more useful. When we think about the calculus, we think about a lot of definitions that help us to move our thought process forward, but they can be tedious. And so we often try to dissect the definition in a way so that we can produce very useful theorems to make our life a lot easier. And of course, you will see that in the calculus. Now, the next one, a personal favorite. We love even and odd in Professor Ron's pre-cal class because with the trig functions, we are tied to even and odd. I told you one time someone recommended removing even and odd functions from college algebra, and I disagreed. I said, if we're going to leave out something, let's find something else. That this is important. And as you know, when we take the trig portion of the pre-cal, the even and odd is central to what we do. So here, what we have is a function, -x cubed divided by 6x squared plus 4. And again, this would be a nice WebAssign problem. It says determine algebraically whether the function is even, odd, or neither. Okay, well, this is, again, a very simple exercise. And how do we do it? Well, I'll just, don't worry about covering this up. You can see that the work is here for all the examples. So first, what is Professor Ron's recipe for even odd? Well, we want to compute the domain. Notice here, and let me adjust this just a little bit, square this out. Yeah, there we go. That looks a little bit better. We notice that the denominator can never be 0. That is, we've got a positive term here, or a non-negative term and a positive term. This can never be 0. And so the domain is all real numbers. So again, what's important with the even and odd is that we have the symmetric domain. That is, if we don't have 2, we can't have -2 because we need the symmetric domain about the origin. But of course, the whole real line is vacuously symmetric. So we're like, okay, that's a check. And now what we want to do is see what happens to the additive inverse. For instance, when we replace x with its additive inverse, how does that affect the function? Do we get something that's actually useful? Well, what we do is we simply replace x with its additive inverse, or -x. So we have the negative of -x quantity cubed and 6 times the -x quantity squared plus a 4. Well, of course, when we cube, and this is something we've talked about with the sequences, when we cube the -1, the -1 survives. So we get the negative of x cubed. We cube the x, and so we have the negative of x cubed made negative. And of course, if we square the -1, the -1 becomes a 1, and it basically absorbs. So here, this is something we've seen before. And now that we've done sequences, maybe this alternating bit is making more sense to you. I hope it is. So now we have the negative of the negative, which of course is x cubed. And then of course downstairs we have 6x squared plus 4. Now you're thinking, maybe I should have just left these in play because I'm going to put them right back in. I thought about that, and then I said everybody's going to look and say, well, you know, why didn't you absorb these? Well, basically, if you want to just skip this and just pull the negative outside, notice this is actually the additive inverse of the original because we start out with the negative. So if you want to just skip this step and move right over to here, we definitely have, in this case, exactly have the original function and its additive inverse. So we need the two negatives, or you can just put them back in. I know here it looks like we go forward to go backwards. So now we see that we actually have the additive inverse of the original function. And so by definition, f of x must be odd. Remember, when the negative factor, so to speak, it's not absorbed, then we have this condition ensuing. That's the definition of an odd function. Of course, that, you know, we know these are very restrictive definitions. If the negative absorbs, we get even. If it factors, we get odd. But these are very restrictive. So most functions do not fall into these categories of even and odd. But when they do, you will see additional support for even and odd in the calculus that will be of extreme use to you. So these are important concepts. Now, this next example, when you do the calculus, I augmented this a little bit. You know, when we think of area or volumes, we think, well, you know, they're positive, but you know, you can zero out area when you think about domains. And when you do the calculus problems, when I teach optimization problems, I use the theoretical significance of the polynomial algebra that you learned in pre-cal. So here, this problem will be done the same way, but you can also look at this and notice that we end up with a quadratic, which you can easily optimize without the calculus because you can find the vertex. But this problem doesn't ask for that, but you certainly could do that. For in this particular case, it says a farmer has 1,000 yards of fencing to enclose a rectangular garden. It says express the area A of the rectangle as a function of the width x of the rectangle. What is the domain of A? Well, this is one of those famous problems that Professor Ron loves to do. And you can see in this particular case that's exactly what I'm talking about. So we want to define the area where x is the width. And of course, we can just define y to be the length, just give it a letter. And so if we have the fencing, which is 1,000 yards in this case, or what was it, yeah, 1,000 yards, then we know that the perimeter of the rectangle could be equated to the 1,000. And so for instance, if we want to write a function of the area in terms of x, we can simply solve for y here. So notice if you divide in this case by 2 to solve for y, we get y is 1/2 times the quantity 1,000 minus 2x. Or you could just start by dividing by 2 at the outset, your choice. And then of course, as you distribute here, we get a 500 minus x. Okay, so that's the length, so to speak. So of course, the area of the rectangle from geometry is length times width. And so we get x times 500 minus x. So what you see here is we have two x-intercepts, 500 and 0. So of course, the midpoint of that is 250, x equal 250. So that tells us where the maximum area will occur because that's where the vertex occurs. Again, I've talked about that so much, you're probably tired of it. Okay, so when you look at this, so remember that, you know, those are good, nice, simple examples for the final exam. So now when you look at this, we can just multiply this. Of course, writing it in this way is actually best for us. We enjoy that. So let me just say this, the h of the vertex will just be the midpoint of the segment connecting 0 and 500, which will be 250. And of course, we have a negative, so this will give us the maximum. And so now we can say area of 250 to find the actual K, if we like. So now we've got this nice representation here. We're good to go. So that's just going to be 250 times 250. So 250. Keeping it factored is what makes this easy. And of course, 25 times 25 is 625. And then tack on 2 zeros. So you get the actual K value, the actual maximum. So this is a nice example. And of course, you'll see this in the calculus, and you can choose to differentiate if you want. But the beauty of this problem is that in the factor form, it's much easier. But of course, the problem required that you actually write it this way. And so now we can say, when is this non-negative? Well, we just stay inside that nice little segment created by the intercepts, which would be between 0 and 500. And so that's a very simple problem, but a very fundamental problem that you should master, and you have already, obviously. But put that back into the memory bank, and make out your little formula sheets. Again, there's a nice formula sheet set of sheets on Blackboard that you're certainly welcome to use, and you may have used for your test. But I know a lot of you like to make your own note cards, which is fine. Now, number 5 is an interesting example which has to do with transformations and how we actually visually think of things, but we can do this algebraically too. It says, suppose that the function y equal f of x is decreasing on the interval 5 to 7. What can be said about the graph of y equals negative f of x? Well, basically, it's what is the function negative f doing? So basically, you think, well, when we execute the negative, that is, we apply the negative to the f, that gives us an x-axis reflection. So when we think about this, we're thinking, okay, well, visually, what would that mean? Well, we know we're decreasing here. That is, if you take any two elements in 5 to 7, where x1 is less than x2, that means the values of f get smaller. As you progress through the interval here, the values of the output get smaller. That's the definition of decreasing. Well, how simple is that? That, again, you learned that in college algebra. But of course, if we multiply by the -1 so that we can get the negative function, or negative f, that will simply reverse the inequality. So now we can just see that for the negative f, as we move from x1 to x2, the values of the output actually get bigger, okay? So it's exactly what you would think it would be. That is, the function increases. So the key here is you can think of this visually, or you can just think of it algebraically. I don't think in this problem it really matters. And of course, it would be nice if you were tutoring someone maybe to talk about both instances as how you could visually see it and how you could actually do it algebraically. Okay, so now let's look at, again, the transformations. I guess transformations are important, but again, when I test you on the final, maybe I'll test you on transformations with a trig graph. You see, so you may find the actual learning outcome is transferred to a trig problem. Again, the test can't be infinitely long. So just remember that even spread, you don't want to spend hours and hours on one topic unless you just don't understand it, but that will tend to be less advantageous to you. Now, for this particular problem, it says find the function, oh, these are English majors, right? That is finally graphed after the following transformations are applied to the square root function. Finally graphed, yes, okay, like it's the end of the world. All right, so basically what this does is it gives us three applications. We're not unraveling the function, which is a harder problem, which you would do if you were graphing a trig function. In this particular case, we are applying we are applying the transformations, which is a simpler concept. So for instance, we start with the square root function here. There we go. We start with the square root function and we apply the upward v shift by 2. So that just simply means that to the function equation, we add 2. So we have the square root of x plus 2. Then we do a y-axis reflection. Again, you know these, you learned these in algebra, college algebra. That is, we replace x with its additive inverse. So that accomplishes the y-axis reflection. We proved that. And then we need to do a right shift by 8. Okay, what does that mean? Graphically, it means we just move the point. We add 8 to all the points. But algebraically, we know that that means we replace x with x minus 8. Okay, so when we do that, we can now distribute the negative, and of course, we'll get the negative x and the positive 8 square root plus the 2. So do not fall into the pit by just being simply careless with these problems. Unfortunately, the mathematics, just like we respect the arithmetic of the unit circle, we have to respect the arithmetic of the transformations. And we found that to be very true when we did the trig graphs. So again, as you work through these problems, don't look at the problem as just being trivial to you. Work it out as you write your test work, work everything out in detail. And again, that certainly helps you because that gives you a nice write-up to present on Blackboard, and then I can check your work and give you good quality points for your write-up. So again, hopefully the write-up is making you be a little bit more fastidious as you work through these. Okay, now, you know, we spent all this time on the conic sections, and you're thinking, that's some crazy stuff, Professor Ron. We already knew quadratic functions, and then we talk about parabolas, but they're one and the same, but we talk about them differently. We still have a vertex, but now we have a focus and a directrix. So, you know, it's all good. So in this particular example, we have a vertex of 2, negative 2, and we have a point on the quadratic of 0, 2, and we're asked to determine the unique function. Now, of course, I don't really care how you do this. You can do this any way you want. You can use the theory of the parabola. The answer will be the same, but since we talked about the quadratic function, at least as an entity by itself, there's no problem in using that construction. So of course, the vertex here is 2, negative 2, and we have a point on the graph of F. Now, of course, we have the completed square form here, a times x minus h quantity squared plus k, which kind of looks like what we did. But now, of course, when we do the parabola, we have the 4p, which kind of takes the place of things. I mean, it's a very interesting way how we connect the parabola with the quadratic function. So now what we can do is replace the h with 2 and the k with negative 2. Of course, to solve for a, we just use the point 0, 2. So we can replace, in this case, x with 0, and we can replace the f with 2. So of course, if we add 2 to both sides, we get 2 plus 2 is equal to a times negative 2 squared. And so of course, we just have 4a equals 4. So a must be 1. So very simple. Now, of course, we've got this with everything filled in. And if you want, I mean, this would be a correct answer, but if you look at the choices, they are multiplied. So we just expand the binomial, good old binomial theorem, now that you know in more generality. So we have the x squared, and we have the 2ab, so to speak, which gives us the negative 4x, and then we have the b squared, which gives us the 4 minus the 2. So this gives us x squared minus 4x plus 2. So again, just basic understanding of the quadratic function. Now, I remember when I did my Smart Pen videos, we found that one of the answer choices for 8 was not listed. So what I did, I just went to the test and I put in an answer choice that would be correct. I found my original software that I used to create this, And once I uncovered it, I thought, well, I'll just go ahead and make that correction. So now, and actually one of your classmates pointed out another problem with the solution. I had worked it out correctly, but it didn't come out well on the paper. So I was able to locate that and fix that. So thanks to Jose for finding that. Now, when we look at this, we have 25x squared plus 9 is less than 30x, and we want to solve the inequality. Okay, well, you know, as I told you before, Professor Ron's lemma will always be something that you can use, even if you don't notice that something is a perfect square. But this is where you kind of see that. You look at the AC, which is basically 25 times 9, which is 15 times 15, if you write this with the prime factorization. And then, of course, the two negatives give you the negative 30. So that's the perfect square. So you're thinking, yeah, this is the a squared minus 2ab plus b squared type thing, and that gives us the a minus b quantity squared. This is just the binomial theorem. So even if you don't notice this, you can still factor this by Professor Ron's AC lemma. It doesn't matter. The result will be identical. But then, of course, you know, you've got something squared being less than 0. I mean, of course, that is never true. So there is no solution. So don't be surprised by that if something quirky like that happens. Now, the next example basically is a graph. And what's nice about it is it's pretty much already set up and good to go. Notice we have what we call a slant asymptote, and then we have the rational part. That is the part that exposes the vertical asymptote. So when you look at this, it's already table ready, so to speak. We look at this and see we have the slant asymptote y equal x, and then of course we have a vertical asymptote at x equals 0. But by virtue of the fact that we have x plus 9 over x, which we can actually write this way, clearly there is no y-intercept because 0 is not in the domain. And then, of course, the x squared plus 9 is never 0, thinking of it written as one fraction. So there are no intercepts. That even makes it easier. And then, of course, if you look at it in this form, you can basically say that, you know, to the left of 0, we get a negative quantity, and to the right of 0, we get positive. So this is trivial indeed. But the idea here is now we know we have to approach x equals 0, again, converging to positive infinity, right? Becoming infinitely large. But then we have to converge to the line, the slanted line, y equal x, and do likewise here. So basically what we see is we have an odd function. If we had to test this for even odd, it would be odd, but that was not the question. You could have maybe done that little extra computation, but don't worry about that. What I did write here is that even though this is simple to graph, this will be a function to which we can apply calculus. Because again, you're going to have a local maximum and a local minimum here that you cannot discern from the algebraic methods. You need the concept of the derivative. And so this is something you will investigate in calculus. And once you learn differentiation processes and minimum and maximum theory involving the derivative, then you can find these actual points of where the actual local or relative minimum occurs and the local or relative maximum occurs. So again, I put a little note here, say some fun stuff to come down the way. Now, again, solving inequalities is something you know how to do and know how to do very well. And number 10, again, is table ready. When I say table ready, you don't have any work to do. You have the inequality to solve, x minus 7 divided by x plus 9. So I'm not interested that every problem be filled with huge amounts of computation. Basically, this requires you to understand what an inequality is in the real numbers and how you use the real number theory to affect the solution. So when we look here, this is already, table ready, so to speak. We have the correct form. And we have our boundary values, that is, where is this function 0 and where is it undefined, mainly 7 and -9. So you can do a very simple sign test here. And of course, I've chosen a -10, a 0, and a 10. So when you check in this region with 10, you clearly get positive. And the other extreme also, because you get the two negatives upstairs and downstairs. But of course, in between -9 and 7, you get negative. Now we're just asked to find where is this particular expression less than 0. And so by this simple sign test, we see that occurs between -9 and 7. So that again, application of the properties of the real numbers, that as long as we have one unit of factors divided, multiplied, we can utilize the properties of the real numbers to actually solve these inequalities without having to do a case-by-case analysis. This does the case analysis for us, and it's quick and easy. You will continue to use this over and over and over as you continue your journey into the calculus sequence. Now, what I thought was interesting here for the next one, these next two problems are actually pretty good. I like them just because they're fairly unique. Again, the rational zeros theorem, which I said before, is a theorem that we work backwards to solve for rational zeros. That is, we don't just start out by blindly trying to find rational zeros by hit or miss. We actually develop a list that the theorem says are candidates. But sometimes we don't even have to do that. We look at P over Q, where P is a multiple of the constant term and Q is a multiple of the leading coefficient. But what I've always said is don't kill yourself trying to make a list when you know you've got some simple ideas from the functions if you just take a moment to observe. So we have 5x cubed minus 9x squared minus 6x plus 8. Now, 1's easy to spot, but you can also see -1 will work. Because notice, this makes a -5 here. This is always negative, so that's a -14. The negative here makes a 6 plus an 8, which is a +14. So -1 works, and you can just throw rational zeros out the window because you don't need it. Now, of course, you can generate all these numbers and spend 20 minutes working on this problem, and then that means you've ignored everything I've tried to teach you in this class. I am never impressed by busy work, and I will say that again. I am never impressed by busy work. If you have to do lots of calculation to work a problem correctly, that's very different. I often do problems during my conference hours that have much arithmetic because it's required. I do symbolic computation, but I never do work that's not required. That's not how I've taught you. So you take the techniques which I've made a big effort throughout the term to teach you, and you apply them. And so now, of course, this is basically this problem. If we have a 0, we have a factor. That is, if -1 is a 0, then x plus 1 must be a factor, as we see here. So now we can use synthetic division using the 0, -1 to reduce the cubic to a quadratic. So we have the -1 here, bring down the 5. 5 times -1 is -5, plus a -9 gives us a -14. Now you see this coming out. And of course, -14 times -1 is a +14. Add 6, we get 8. And then of course, -8 plus 8 is 0, which basically verifies this calculation. So now we see that we have x plus 1 times 5x squared minus 14x plus 8 right here. Now, of course, this is where we can use Professor Ron's AC lemma. You're thinking, well, either this quadratic has rational zeros or they're not. Not a difficult question to ask. And so if we use the AC method, notice we have the 5 times the 8, but we can actually break up the 8. We need a what here? We need a -14. So we're certainly not going to get it with 5 and 8. That clearly doesn't work. So we can look at this as a 2 times a 4. and get a 10 and a 4, and then of course insert 2 of the negatives to give us the negative 14. So this is an excellent example of utilizing techniques which I have taught you. And so now using the AC method, we can factor by grouping. We can just write the middle term as negative 10x minus 4x, and then factor the first two terms with the GCF of 5x, and the second two terms with the GCF of negative 4. And then of course the x minus 2 being the common factor, and then the 5x minus 4. Now, of course, by zero product, well, we already know this one. We get a negative 1, a 4 over 5, and a positive 2. But we could also just kind of beat this to death and do a complete factorization based upon the fundamental theorem. That is, we can factor the 5 and have the x minus c1, x minus c2, and x minus c3. It's just a little additional. The problem didn't require this, but it's also nice to know that you can theoretically always do the complete factorization. And this just gives us the A here, and then of course the product of all the factors containing the actual zeros. So you did so much of this, you're probably tired of this, and that's okay if you are. Now, for number 12, this is basically repeating 11, but again, a very important concept. It says use the factor theorem to determine whether x minus c is a factor of f. So this is the same thing we did before. We got x minus a negative. So we need to check to see if negative 11/5 is actually a zero of this polynomial. And of course, I was good to you when I chose this problem because it doesn't require lots of horrible factoring and fractional arithmetic. When you bring the 5 down, notice the 5 absorbs into the 15, and you get a 3, so a negative 33. A negative 33 plus 23 is a negative 10. And now when you look at this, the 5 absorbs into the negative 10, giving us a negative 2. So a negative 2 times a negative 11 is a positive 22. If we add the negative 42, gives us a negative 20. So the numbers work out very nicely. And then of course the 5 absorbs into the negative 20, giving us a negative 4. And negative 4 times a negative 11 is a positive 44, which added to negative 44 gives us a 0. So this is exactly what we did here. These problems are basically identical, even though they don't look that way. And of course, if this particular real number is a 0, then of course this must be a factor. And of course, that's what we wanted to show. So again, the simple theorems in the theory of polynomials is important, and you will continue to use this in calculus over and over. Now, let's look at number 13. And of course, this problem basically just says, draw the functions, the function and the inverse and whatever, and domain and range. So let's just look at this. F of x equals the square root of x minus 2. Now, of course, this would be easy to show one-to-one using the definition of one-to-one, which we did, but you won't have to affect that in the WebAssign. You could actually write that out in your test work. That'd be nice to see, but it's not required. Again, I'm not going to ask you to compute the inverse of a function that doesn't have an inverse. So this is a one-to-one function. So we can easily compute the domain here. And obviously, the domain and ranges just switch between the function and its inverse. So of course, this makes sense for 2 and greater because of the radical. And then of course, the principal square root has a minimum value of 0, and then of course shoots off to infinity. So basically here, we just flip these for the domain and range of the inverse function. And okay, what I've done here is I've got a little simple sketch of the functions here, but it would behoove you. For instance, this is a right shift by 2 to give you the square root here. That's easy. But just as a little practice here, let's just go ahead and solve for the inverse function. So we can square this and get y squared is equal to x minus 2, and of course solve for x. So x is just y squared plus 2. And then of course, we like to be able to graph these on the same set of axes. So we select the x as the independent variable. And so we get x squared plus 2 as the x version of our inverse function. And then, of course, with this property of using the same independent variable, we get this nice reflection through the line y equal x. And so again, a very simple graph of f and f inverse. Okay, so again, very basic stuff. It's unfortunate we spend half the course reviewing college algebra. If I had my way, we wouldn't do half of this, and I teach you more stuff to get you ready for calculus, but that may change. That may change because review is good, but for some of you, the review makes you lazy, and you're thinking, I don't need to study. And once you hit trig and the conic sections, you find that not to be the case. So let's look at the next example. So we have, that was page 3, page 4. A personal favorite, of course. Now, what I like about this problem and what I've said when we do problems in WebAssign, you can choose a logarithm base that will help you if you need to do an approximation, so you don't necessarily have to change the base. So what the problem says is write in terms of natural logarithms. So what we can do, as opposed to maybe taking a base 4 log or a base 5 log to just undo these, we can just use natural logs. And then, of course, the power rule. The power rule is that identity that just kind of makes us feel good. When we're doing the laws of exponents, we have the corresponding identity power rule for the logarithms. So of course, if we take the natural log of both sides, the power rule will remove the power x plus 4 and 2x plus 5 to the coefficient status. So we have x plus 4 times the natural log of 4 equals 2x plus 5 times the natural log of 5. Now, of course, what we can do is just distribute. So we're going to get an x times an ln of 4, and we're going to get a 4 times an ln of 4. And of course, here we'll get an x times a 2 ln 5. So notice I just move all the riffraff over to the right and isolate the x. And then, of course, 5 times ln 5. So it's easier kind of to see what's going on solving for x. So now we can retire all of our x terms to one side. So we've got the ln 4 term, and we subtract the 2 ln 5 term here, again multiplied by x. And then, of course, we transpose this term to join the 5 ln 5 and negative 4 ln 4. And then, of course, we can divide by the coefficient of x to get x equal 5 ln 5 minus 4 ln 4 divided by ln 4 minus 2 ln 5. Now, again, this will be very useful in the calculus, and we see that regardless of the base you use, you're still going to get an equivalent answer. So the logarithms are really mysterious functions, but very useful functions. And when you get to Cal 2 and you see that you can write pretty much all the elementary functions in terms of the power series for the exponential, and then utilize the geometric series, and then use the definitions of the hyperbolics. I mean, all these functions are related. And the neat thing about it is that you would think that would make math so simple, but it's all these interdependencies that make math a little bit more complicated. So the fact that everything works out, I guess, makes math a little more challenging, but certainly very useful. Okay. So good old logarithms. Seems pretty simple now after we've done trigonometry. Now let's look at page 5. These are all nice and spread out, so it looks like we're doing a whole lot more than we are. The next problem is solve the equation. So this is just a basic log equation. You'll have maybe 2 or 3 of these to do on your final. We have the base logarithm, base 4 logarithm of x squared minus 3x equals 1. Okay, so this is very standard. We don't even have to use any fancy identities like we did in the last problem. What's a logarithm? It's a power of the base. So the power of 4 that equals x squared minus 3x is 1. So x squared minus 3x is just 4 to the first power. And then, of course, the problem says, be careful, don't give a solution that it really doesn't work. So now, of course, we have x squared minus 3x minus 4. And then, of course, this is a simple factorization using -4 and 1. And of course, that sum of those zeros gives us the -3. So that's a at side factorization, not requiring the grouping. And then, of course, by the zero product, we get a 4 and we get a -1 for x. And so basically, we just have to make sure, this square kind of saves us in both cases. With the square here, the 4 is actually valid and the -1 is actually valid. So both values, as I've written here, are valid. So they can both be included in the solution set. Just remember to always check with the logarithm equations that the values that you get for the independent variable do indeed solve the original, and do not include ones for which the original is undefined. That's, again, something you know very well. Now, this is an example where you basically get to do your transformations. That is, I test you on transformations usually with a trig graph, and that covers all the bases, so to speak. Just remember, the semester tests are actually more specific because we have less material, and I can cover topics with 2 or 3 problems. Whereas on the final, we're lucky to get one problem or a problem that contains 2 or 3 topics. So again, because it's comprehensive, it's more of a survey. So remember that as you take the test. Now, notice here, we want to graph y equals 2 times cosine 1/2 x plus 2. Well, this is a nice transformation problem. The parent function, of course, is cosine, and it's nice. I mean, when you do your power series, you'll also do the transformations. When you establish a set of Maclaurin series, which are basically functions on the intervals of convergence, you can use all these transformations, and you will see this again. And the beauty of it is, if you spent the time in this class, when you actually do it, you'll know exactly what you're doing. That's the key. The math does not change, ladies and gentlemen. Even if you're doing calculus, the transformations are still valid. So this is going to be a big plus when you get to these concepts in the calculus. So of course, first, notice if we replace x with 1/2 x, we do the stretch because 1/2 is between 0 and 1. So now we have an h stretch by 2, the reciprocal of 1/2, as I've taught you. So that's going to make the period bigger. And now, of course, to get to the next step, if we look at this, we need to see how we can incorporate the 2. Well, that's just going to multiply the function by 2. So that's going to be a v stretch by 2. Very simple. 2 cosine 1/2 x, or cosine of 1/2 x. And then the plus 2 is just an upward v shift by 2. So again, the last one is very simple. So this gives us 3 transformations. Now, of course, you can sometimes shortchange this and say, well, I know the period's going to be twice the original period. So it's going to go from 2 pi to 4 pi. But as I've taught you, you can also just write down the principal points here for the cosine function, again, as we've listed here. And then, of course, affect the first transformation by multiplying all of the x coordinates by 2. So, of course, that'll give you a 0, a pi, a 2 pi, a 3 pi, and of course, the 4 pi gives you the 0 to 4 pi, which is the new period. Okay, so all of this will be borne out here. Again, at this point, it's pretty simple. This is just to give you some nice simple points to dot in a graph really fast and be done with it. And so now we want to do a v stretch by 2. So we just add 2 to all the y coordinates. So in this case, multiply all the y coordinates by 2. So we get a 2, a 0, a -2, a 0, and a +2. So multiplication by 2. And now, of course, we add 2 to get the upward vertical shift. So again, add 2, 2 goes to 4, 0 goes to 2, -2 goes to 0, 0 goes to 2, and 2 to 4. And so now this gives you the new graph right here. So you can grab 0, 4, and of course you go ahead and do your equally spaced x values from the principal points. You have your 0, 4, your pi over 2, pi 2, you have your 2 pi 0, 3 pi 2, and then 4 pi 4. And there's your period right there, just as I taught you. Very simple. You will use this over and over again. And when you get to polar coordinates in calculus, you'll do most of this in your head to do a little simple sketch and then move to a polar graph. So this gives you the added detail. And then as you get more and more esteemed in your understanding, you can do a little less of this to go ahead and get a quick graph. But you don't want your graph to be wrong as you move to the polar graph. So you can check a couple of things to be able to do this. Basically, just dividing the principal period by 4 gives you these principal points here. That makes drawing the graph very simple and something you probably remember from when we did this. Now, the next problem, again, you know I like the inverse trig functions. So it says find the exact value of the inverse cosine of 4 pi over 3. Well, of course, we know that the inverse cosine, in this particular case, the output lives between 0 and pi. So we can't apply the inverse equations and say this equals 4 pi over 3 because that's not in the range of the inverse cosine. So we can apply the arithmetic of the unit circle. Clearly, this is bigger than pi, but less than 3 pi over 2. This is in the third quadrant. So we can apply the reference angle, which in this case will be what? Pi over 3. Pi minus this gives us pi over 3. And of course, in the third quadrant, the cosine is negative. So we need the negative here. And then, of course, to work with the negative, the inverse cosine is not even, but I gave you this identity. This is actually pi minus the inverse cosine of the non-negative, so to speak, input. That we can absorb this and use the arithmetic of the inverse trig function. And so now here we can easily apply the inverse rules because pi over 3 is in the output of the inverse cosine function. So again, this was a very useful identity that we utilized in our study of the inverse trig functions. And now, of course, we just get pi minus pi over 3 or 2 pi over 3. And again, remember, you know, you're thinking, why do we do this? Well, when you get to Cal 1 and Cal 2, especially Cal 2, you will be utilizing the inverse trig functions. And you will be grateful that we even talked about them in this class. Now, for number 18, it actually specifies that x is positive and in the domain of the inverse trig function, which you automatically know. You actually will find with this problem that it will not be required for x to be positive, which I'll notate to you. We just simply want to write an algebraic expression of sine of the inverse tangent of x. So as I've written here, it's also valid for the other output interval of the inverse tangent. I just wrote that here. So this is really not required because the sine is always going to be held by the factor of x there. So it's not required that x be positive. But I think, you know, there are times when instructions get pushed forward to simplify the process, especially with a triangle. So now, of course, to do the sine of the inverse tangent of x, we make the assignment that we always do. We want to think about this as an angle of a right triangle. So we can assign the inverse tangent to be alpha. And of course, applying the tangent function will give us x is equal to the tangent of alpha. So of course, the original problem will just be sine of alpha. And of course, you can use the Pythagorean identities, or you can just give yourself a boost and say, okay, well, tangent of alpha is just opposite over adjacent, and then use the Pythagorean theorem to get the hypotenuse, which will be, of course, 1 squared plus x squared square rooted. And so now you can simply apply the right triangle to this trig function. Sine of alpha will just be opposite over hypotenuse. And of course, the sine of this function will be carried by the x. So this, of course, would be valid here also, not just here. So again, a type of problem we've done many times, and we've done problems much more complicated than this using the addition formulas and subtraction formulas. Again, if you have mastery of those, you will find the problems on the test final to be very straightforward, which is exactly what I want them to be. Now, For number 19, we just have a basic trig equation that is, and the problem gives you a little boost. They say, well, just solve in 0 to 2 pi. You can always solve for all solutions and then just restrict to the given interval of the problem. So we have 2 sine squared equals sine x. This is a nice factoring problem. So of course, if we retire everything to one side, we'll get 2 sine squared x minus sine x equals 0. And then of course, we're like, you know, we like zero product. So let's factor a 2 sine from both of these. So we got the 2 sine x, which leaves behind the sine x. And then of course, with the 2 here, we have a minus 1/2 left behind when we factor this term. And then of course, by zero product, we don't care about the 2, that won't matter. We just have sine x equals 0 or sine x equals 1/2. Of course, this is our friend. This is right on the x-axis. So this would just be multiples of pi, where k is an integer. Again, now you can do this in your head. Then we can use Professor Ron's lemma. We have sine x is equal to 1/2. And of course, the inverse sine of 1/2 is pi over 6, which we can extend by multiples of 2 pi. And then Professor Ron's lemma, since we're in the upper arc, pi minus pi over 6 is 5 pi over 6 to give us the other solution in the upper arc, which we can extend by multiples of 2 pi. So I wrote here Professor Ron's lemma. Do not leave this out. Then you leave out half the solutions and the problem is wrong. So please don't fall into that category. When I've solved the equations, I've been very fastidious, and you need to keep that mode. If you want to have success in STEM mathematics, you have to be more particular and quit relying on fancy gadgets. Let your brain help you out. That's probably something you can depend on much more than a fancy gadget that you probably overpaid for. Now, when you look at this, we can say, okay, well, let's just see. Let's just start going. Well, 0 is in this category, and pi, so we got those 2, but of course 2 pi is too big. And now we just look at these and say, well, pi over 6 is good and 5 pi over 6 is good. But if we add multiples either way to 2 pi, we go outside of this interval. So we only end up with 4 solutions there. So again, always look for all solutions when convenient, and then restrict if you have a particular interval where the solutions need to exist. Okay, so again, a very standard, straightforward problem that basically focuses on the fundamental techniques. And of course, if you go through some of your old quizzes and trig equations that involve, you know, identities and other things, you will find that you're more than prepared for this. So I think all the work you spent on the trig will now pay off handsomely. Now, this next problem is an exact computation problem, and I was going to try to factor it in a neat way, but it really didn't factor. So much for that. It says the distance from home plate, this is a law of cosines. And again, you know, I'm not a big fan of the triangle theorems. You know that. I spent more time. I mean, I love the triangle theorems, and I forced you to do exact computation, which a lot of you didn't like. But if I'm going to tolerate it, it's got to be done right and done correctly. So this, of course, is law of cosines, which I will be addressing in your signature assignments. That I've got to grade them with a rubric from the college. So that's why I will be doing that this week while you're taking your final examination. So it says the distance from home plate to dead center field in Sun Devil Stadium, I think that's made up unless there is a Sun Devil Stadium, is 401 feet. It says a baseball diamond is a square with a distance from home plate to first base 90 feet. How far is it from first base to dead center field? Okay, well, that's just a triangle. And of course, since we have a square here from home plate to first base, and then of course direct into center field, we basically cut the 90-degree angle into two 45-degree angles. So this is just a law of cosines. It seems hard, but it's quite simple. And so with that, I should say the triangle theorems are nice. They're certainly good in engineering and physics. And so of course, we'll just have the c square, let's call it a d, c square equals a square plus b square minus 2ab cosine theta. But of course, cosine of 45 is 1 over root 2. So to make this manageable, we just see here that the root 2 will absorb into the 2 to give us a root 2. And then, of course, I just factored this, but there's no pretty numbers here at all. So you get a 400 times a 400 minus 90 root 2 plus the 90 squared. And I just said, go ahead and round to 1 decimal. And I use my Google calculator once I take the principal square root. So here's an exact value here, which is actually what we want if you're doing any type of computation. I'll be looking for this on your signature assignment. And then, of course, with Google, we can get a nice calculus approximation into 1 decimal, 343.33. So again, very simple problem, but again, utilizing the trigonometry of the triangle. So law of cosines. Now, the next problem, it says use the center, vertices, and asymptotes to graph the hyperbola. Well, of course, if they give you a picture, you know, WebAssign says, okay, well, give me the vertices, give me the foci, or whatever, give me all of this stuff. So you know how to do that. So basically what I did is I took the example here. This is just a translated hyperbola. We say that the translation equations, x prime equals x minus 2 and y prime equals y plus 1. So we get nice translation equations here. And then, of course, from this, we know that h is 2 and k is negative 1. And then, of course, the square term gives us the a, and the negative term, or the term with the negative, gives us the b. So we have a is 2 and b is 3. So we can go ahead and construct the, in this particular case, the asymptotes. Again, in the translated system, we have y prime is equal to plus or minus 3/2 x prime. But of course, if we want to write these in the non-translated system, or basically in the old system, we use our translation equations. We just replace y prime with x plus 1, and we replace x prime with x minus 2. You do this the same way with rotation of axes. It's the same type of concept. And then, of course, with the plus, we'll get y equals 3/2 times x minus 2 minus the 1. And then, of course, if we add the terms, that is the 2's absorbed. And here we've got a negative 3 minus a 1, which gives us the negative 4. And of course, the 3/2 x. And then, of course, if we take the negative, notice here, we get the positive 3 minus the 1, which gives us the 2. And of course, the negative 3/2 x. So we can go ahead and label the actual asymptotes. But now, of course, when we look at this and when we think about what's going on here, the center, again, is 2, negative 1. And you can use your translation equations to actually find the 2 vertices here. Of course, b prime would be plus or minus a0. And then with the translation equations, we need to add to that 2 as we do here. And then, of course, add the 0, the negative 1, using the translation equations. So that's going to give us vertices of 4, negative 1, and 0, negative 1, which you can easily plot. Or like most of you, you just go to the center and you go 1, 2, 1, 2, which is fine. And then when you want to find the B, you go up 3, 1, 2, 3, and down 3. So that's fine. That's not an issue here. So now, of course, you can draw your box, and then you're good to go. Just remember also that c squared equals a squared plus b squared when you do your foci. So remember, c squared equals, I'll use this in the rotation problem when I get to it. So I won't say so much more about this for the foci. So again, the hyperbola, you didn't have to complete the square. Probably I'll have an example where you need to complete the square kind of to cover all the bases. Just to, again, it covers everything, all the important aspects about the conic sections. Now, the last few problems have to do with, again, the geometric. The arithmetic sequence is simple. It's kind of fun. There did some examples in conference hours where we got a quadratic to figure out the n, and those arithmetically can be more involved because you're using Professor Ron's AC lemma. But the theory behind it is very simple. The more important, even though I want you to know how to do that, the more important sequence that you will use often in calculus will be the geometric. So review the arithmetic and its definition. You will be tested on that, but also spend time on the geometric as it is very significant. Now, we've got find the indicated sum. We have I equals 1 to 5 of 3 times 3i. Now, of course, we have a convention when we do these problems, ladies and gentlemen. What we want to do is write this in the form, again, you can expand it or you can write it in the form of the derivation that we did. That is, we're starting at 1, which is good. So we simply, in this case, just borrow a 3 from the 3i to get 3 to the I minus 1, because that was the formula that we derived for the general term. And then, of course, that will be a 3 times the 3 to give us the 9. So this is now our convention formula, so to speak, for the partial sum in this particular case. When we look at partial sums and we think about how they're done with the binomial series, we start at 0. But when we actually write these from the convention that we established in our book, we start at 1. So of course now this was going to be, again, as we reach up to here, this gives us the 5, which goes into our partial sum formula. That is 1 minus r to the n, and then 1 minus r, of course, where r is 3 and a is equal to 9. So again, remember, this is a times 1 minus r to the nth power divided by 1 minus r, where in this case, the n is 5, as we see from our generalized formula for the sum convention for the geometric series. So again, if you want to use how the theory that we derived in class, you need to make sure that this form is correct. Just like when we did that bouncing ball, you can't just make assumptions about things, especially when your formulas are contingent on how you write this. And so now we're good to go. The hardest part is just making this change or writing it in a way that you know how many terms you have. And so now what we see, if we just actually multiply and divide by -1 to flip these around, because that's negative and that's negative, we'll get 3 to the 5th, which is 243, minus 1. And of course, the 3 minus the 1 gives us the 2. And now, of course, the 2 will absorb into the result here. That is, this is just 242. And so that'll give us a 121. And of course, multiplication by 9 gives us the 9, and then the 18, and then the 9 plus 1, which is 10. So 1089. So again, remember, this is 4 terms utilizing the convention that we established when we derived the sum for the formula for the partial sum. Now, keeping in mind of that, the next problem, number 23, actually gives us an infinite geometric series. That is, it doesn't even write it in the sum form. It just gives you the first, the second, the third, and the fourth term, and then the ellipsis. So what we can do with this is just go ahead and construct this like we did here, but this is written out where this one wasn't. So now what we can see is that the first term of the a is 5, and then of course to get to the next term here, we're multiplying by -1/4. So now you can see that r is -1/4 and a is 5. So this is the infinite case, which is actually infinitely simpler because you have no n. You just have a over 1 minus r. So students love the infinite case. So now, of course, like I said before, we write this in the form that suits this and let n pass to infinity. And so now we've got the a divided by 1 minus r. So that will be 5 divided by 1 minus the negative. Again, since r is -1/4, this is an alternating series. It alternates plus and minus in the terms. And then, of course, this is 5 divided by 5/4. Reciprocate and multiply, the 5's absorb, and we get 4. So the geometric is a very, very useful linchpin in calculus. And like the Pythagorean theorem, it is indispensable. So you will do well to remember what you know about the geometric, and then when you get to Cal 2, you'll hit it big and you'll use it throughout the chapter on infinite series, especially when you get to power series. Now, the 24, remember I did an example like this in class where we want to use induction, and they give you a nice little hint right here, but you don't have to use this so much, just do it the way I did it in class. You've got a nice hint like this in your WebAssign. Again, work out the WebAssign problem and then go back and fill in the blanks. Lots of times what the WebAssign has you to fill in will make more sense once you've actually worked through. And then once you've worked through it, you can look at their formatting and apply what you know and select or respond correctly. Again, the WebAssign does a nice job of testing you on proofs, but you do have to make a concerted effort to formulate a strategy and then work with the WebAssign questions. So now, just like we did in class, it says use the principle of mathematical induction to show that 5 is a factor of 7 to the n minus 2 to the n. And again, you're thinking, all right, well, we've already done this, Professor Ron. And what I've done here, and I wanted to write this out a little bit more cleanly. So what I'd written initially was bad, so I erased that. But we have a p of n, which is 7 to the n minus 2 to the n, is a multiple of 5 for n greater than or equal to 1. That's what we're assuming to be the logical statement about natural numbers. So that just means that 5 divides this, or as we write this algebraically, this is just 5 times some integer, some positive integer. Now, again, this is where the induction principle is extremely valuable. You know, you can check 4 or 5 cases and think, well, yeah, this works out. But that, as I was telling some students yesterday, you can actually construct formulas that'll work for a finite number of natural numbers, but fail after a particular limit is passed. And that can be surprising. So you can't just make the assumption that it works. Induction kind of gives you that additional boost to say that regardless of the natural number you pick here, it will be a multiple of 5. So let's apply the induction principle. We start out with n equal 1, so we replace n with 1, and we get 7 to the first power minus 2 to the first power, which is 5. In any book, 5 is 5 times 1. That is a multiple of 5. A number is always a multiple of itself. So P of 1 is true. Now, again, the Dr. Stewart always switches to K, but we remember when we proved the binomial theorem by induction, we didn't do that because K was already in the formula, and we saved ourselves some agony by doing that. But I went ahead and used the same setup that Dr. Stewart does. So we assume that 7 to the K for some natural number minus 2 to the K is actually a multiple of 5. So I just wrote this as 5t, where t is some natural number. That's our induction hypothesis. And like I did, what I tried to do was go ahead to the hint and factor it like this as it's written in the hint, but that makes no sense because I said, well, let me just use the hint. And then I'm like, no, they won't see this. You have to write it this way, then the hint falls out. Because if you don't write this step, you don't really see where this comes from. So that's the reason for that. I thought, well, I'll use the hint directly, and then I'll be sure to tell them to do this like I did in lecture. So add and subtract the convenient term. The idea is that we've got to use this, and we don't have 7 to the K and 2 to the K. We've got K plus 1. So the quickest way to move this problem forward to get to the hint is add and subtract 2 terms that will introduce the 2 to the K in a way that we don't overdo it, because we've got 7 to the K plus 1. So common sense says try 7 times 2 to the K, add and subtract. Because now if we do this, then we can group and factor that way. That is, we can extract a 7 and have the 7 to the K minus 2 to the K, which is covered by the induction hypothesis. Now, what about what's over here? Well, this is even easier. We can factor 2 to the K, and that leaves behind a 7 minus a 2. And of course, that's a 5 right there. So we get that for free. And that's exactly what the hint says. But you don't see that unless you write it this way. So now notice, again, if we don't use the induction hypothesis, we did not use induction. So sounds like real astute comment, right? You know, it's like, I don't know, if you didn't drive down Highway 45, then you didn't drive down Highway 45. Sorry, you know what I'm talking about. So now we can say, okay, this we can replace with 5 times some multiple, excuse me, 5 times some integer, t, whatever it might be. And then of course, this is 5 times an integer. And so when we factor the 5 here, we have a 7t plus 2 to the k. Both of these are integers. 2 raised to an integer power is an integer, again, a positive integer, and 7 times a positive integer is again an integer. So these are natural numbers. So this is again saying that 7 to the k plus 1 minus 2 to the k plus 1 is indeed a multiple of 5. So p of k plus 1 is true. So therefore, we satisfied both of the requirements of the induction principle. We verified for some initial value of n, usually it's 1, but not always, and we verified for an abstract value of the natural numbers and showed that we get the domino effect. That is, if we assume it true for k, we automatically get the truth for k plus 1. So that just covers everything due to the arbitrariness of this k. And therefore, by induction, this is indeed true. So you can see with divisibility when you're doing arguments about natural numbers, and like I said, some of you will take some number theory, the induction is very powerful. Just remember, the induction doesn't derive a formula. It's not the basic derivation that we do, like we derived a formula for the sum of the geometric series, the partial sum. We can get a sum, we can get a formula and then verify it by induction. Again, induction is one of those things where, okay, you don't really have the algebra backup, you have the cases that you've checked, and you need a verification method, and that's what this does. Like I said, there's some purists that say, well, if you do it algebraically, then you have to do an induction proof to just top it off, so to speak. Again, the idea is that whatever you use, you want in a math problem, you want to make sure that it is indeed valid. Okay, the last problem is kind of like covering the binomial theorem. So again, how could Professor Ryan cover the binomial theorem? Well, this says, in this particular case, find the coefficient of x to the 4th in this expansion. So this doesn't mean that you want to write out the entire expansion. It just means that for x to the 4th term, go ahead and write out the sum. That is 3x plus 4 raised to the 6th power. That gives us an n of 6. So k runs from 0 to 6, giving us 7 terms. K, 6, choose k, and then of course we have a raised to the n minus k, 6 minus k, and 4 raised to the k. Now, of course, when are we going to get the 4th power here? Well, that's going to be where 6 minus k is equal to 4, or k is equal to 2. So what you can do here is just compute the k equal 2 terms. So we go into the sum and we just compute k equal 2. So that's 6 terms, 6 choose 2, 3x to the 4th, 4 to the 2nd power, and just run that through. Now, you don't really have to drag the x to the 4th along, but since I wrote it here and I didn't think it made sense to leave it out, I went back and stuck it in again, because we need the coefficient, and this is the k equal 2 term. So first we do the following factorial, 6 choose 2, that'll be 6 times 5 divided by 2. And then of course we have 3x to the 4th, which will be 81x to the 4th. So 81x to the 4th. And then of course 4 squared, which is 16. And now what I did, again, the 2 absorbs into the 6 to give you a 15. So that gives you a 15 times 16 plus 81. But of course, 15 times 15 is 225. So you're thinking, okay, this will just be 15 times 16. So this will be 225 plus 15. Just add the additional factor of 15. And 80 is just 80 plus 1. So these are simple to multiply. So now 225 times 80, and then we have 225 times 1, and then we have 15 times 80, and then 1 times 15. Easy numbers. So the 80 here, you just go ahead and multiply 8 times 225. That gives you the 1800 with the additional 0. The 225, 8 times the 15 gives you 120 with the additional 0 and the 15. So doing the symbolic calculation here is easy. So now this gives you 18,225 when you add these. And of course, this gives you 1215. And then when you add up these numbers, you get a 5 and a 5, which is a 0, 10. Carry the 1, that'll give you a 4. And then you have another 2 and 2, which is a 4. Then you have an 8 and a 2. Excuse me, in this case, you have an 8 and a 1, which is a 9. And then a 1 that's left over here from the 18,000, giving you 19,440. And of course, for the x to the 4th. So with the coefficient, basically, you just pull off this part. So just remember, if you're asked to do a coefficient, then fine, don't put in the variable part. But if it doesn't say, it just says find this particular term or whatever, then you can include the x to the 4th. But notice here in this particular problem, this is a formatting issue. So it says find, in this particular case, here we go, find the coefficient of x to the 4th. So what we see is just the coefficient. So that's a formatting deal. So when you actually would write this, you could say coefficient of x to the 4th is 19,440. Okay. So what you're seeing with the new material is that it's not unreasonable in the sense that it's difficult. It just basically, the test will be survey-like, and so review new and then make sure you've got that on a comfortable level, and then go back and review any aspects where you feel that some rust is set in. And if that just means spot checking a couple of quizzes or whatever, then that's all you need to do. There's no need to do excessive studying. I can remember every time I had a final exam, I always spent most of the time on the new material because I knew the other material. I've been tested on it. And so I thought, all right, this is good. I'll get this new material down. And then I'll go back and spot check. Maybe I'll just work through a practice test and I'll be good to go. And if there's some bumps in the road, then I'll focus a little bit more on a particular topic, maybe go back to lecture notes or look in the textbook for some good review examples and things like that. Maybe go listen to another lecture. But Professor Ron talks about, I don't know, what was it, ellipses or something. How do I figure out the major axis or something like that? Now, what I wanted to do is say a little bit about rotation of axes. So I wrote some things up here. The idea about rotation is we think of it almost like translation, and I thought this would be a good way just to end the class, to give you some of the ideas here. And I wrote this up. I've got extensive notes on this, but I wrote this up this morning to give you an idea of how we can talk about rotation of axes. Now, this looks complicated, but it's not. Notice when we do the translation of axes, and of course, when you take linear algebra, you're going to do this a different way. When you take the translation, you basically just translate the center to HK, and you get x prime equals x minus h and y prime equals y minus k. And those are fairly straightforward equations, and then you can work them backwards. Well, with the rotation, what we do, and there's a little bit more theory involved here that's not so simple. Let me just apprise you of this. This is why we don't always have time to cover this topic. The idea here is that we think of the original axes here, and then we think of a rotated system by some angle theta. So we take the original system and rotate, as we've done here. So the new system, like we had before, is the X prime, Y prime system. But we just set up two simple triangles. What we do is we take a point P of XY in the old system, and then the P of X prime, Y prime in the new system. So how do we affect that? Well, when we draw in the new X prime, we now create another angle from X prime to the actual radial distance from the origin to the specified point. And we call that radial distance rho. Just give it a letter. That seems to be a popular letter for this type of computation. Again, if you do this in linear algebra, you do it much differently from this. But what we can see here is that now we can look at a right triangle relative to the XY system, and we can look at a right triangle relative to the X prime, Y prime system. And so what we can see is, okay, well, we need a label for this angle, so I'll just call it phi. So for the first triangle here, and I get, well, here's what I wrote here. Let's just look at this, and then we'll move to this. For this triangle here with the phi, we're going to have this distance, X prime, will just be what? Rho times cosine of phi, right here. And this distance, Y prime, just using the sine function, will be rho sine phi, right here. And then it's like, okay, well, that's the smaller triangle, so to speak, that it has the angle phi. And then when we look at the XY system, the angle is now theta plus phi, so we get to use our sum formulas. Now, when we look at, well, it's basically here, when we look at this particular distance for X, this will just be rho times cosine of theta plus phi, right here. And then the Y right here, we'll use the sine function, will be rho times sine of theta plus phi, which we have right here. So again, this construction just helps us to elucidate the right triangles. And now you can see how we can work this out. Notice the X, we just use the sum formula for cosine, which is cosine theta, cosine phi, minus sine theta, sine phi. And then, of course, when you multiply this, you can see these occurring. So we get a rho times a cosine phi right here, and we get a rho times a sine phi right here. And so we can do a replacement. So we just get X is equal to X prime cosine theta minus Y prime sine theta right here. Now, likewise, so you're thinking, well, you know, Professor Ron, all we really used is the addition formulas. Now, when you look for the Y here, we're going to use the sine addition formula. So we get sine theta plus cosine phi plus sine phi plus cosine theta right here using the addition formula. Now, when we multiply, we've got that rho times the cosine phi right there. That's going to give us the X prime. And we've got the rho times the sine phi. That's going to give us the Y prime. So now Y, the old system, will be X prime sine theta plus Y prime cosine theta. Now, so this is kind of like the backwards of what we had. You know, I always write down the X primes first with the translation equations. So this gives me the X and Y in terms of the new coordinates. Now, of course, I would really want to be able to go in the other direction too, because again, this is very useful, but I'd also like to be able to go in the other direction if that need arose. And so now what we can do is take the two equations here and stack them, and then just multiply by convenient powers. For instance, if I want to solve for X prime here, I can multiply the first equation by cosine theta and multiply the second equation by sine theta. And of course, what's going to happen is that this is going to be, these will be equal and opposite. So when we add, they absorb. And then, of course, in this case, this is just X prime times cosine squared plus sine squared, which is 1. So I get X prime is now X cosine theta plus Y sine theta. Just combining these, with a convenient multiple. So this gives me now x prime in terms of x and y for the rotation angle theta. And now here I look at the same thing and say, well, I need to solve for y prime. So how can I get rid of this? Well, I can hit this with a minus sine theta and do a cosine theta on the bottom. So now when I hit this with the minus sine theta, I get the minus x sine theta. Then I get the minus x prime cosine theta sine theta. And then of course the y prime negative negative give me the sine squared. Likewise with the cosine here, these terms will be equal and opposite. And again, I'll get the cosine times the cosine, which is the square. You add these up, you just get y prime. These absorb, and you're left with what? X times sine theta plus y times cosine theta. These are actually orthogonal matrices. Their inverses are their transposes. But again, that's a linear algebra question, which you will answer when you take linear algebra. So now, ladies and gentlemen, we have the same thing that we had for the translation. That is, let me just put these below. For the translation, we have x prime equals x minus h. We have y prime equals y minus k. And of course, it's easy to solve for these by transposition. X equals x prime plus h, and y equals y prime plus k. So we see the translation equations are a whole lot easier. So we call these rotation and these translation. Of course, the rotation are a little bit more complicated. There's a lot more theory going on, but now we see that we're doing the same thing in each case. So we've got our nice translation that we've used many times, and now we have rotation. Now, one thing that's very important here, and this is something that's that requires a lot of theory, so to speak. So I actually drew this twice to get a nice picture of it. When you actually, and I'll show you my notes here so you believe me, when you actually do the substitution here, you can actually find the rotation angle, which makes the actual B prime coefficient from the standard equation. For instance, this BXY is called the cross product term. That means you have a rotation and you want to eliminate this. And so how can you eliminate it? Well, once you do the substitution here for X and Y, you get new coefficients and you want to zero this out. And so in order to zero this out, you need to set theta to be 1/2 the inverse cotangent of A minus C divided by B, these being the coefficients that you have here, A, B, and C, the X squared coefficient, the XY coefficient, and the Y squared coefficient. So that gives you a way to actually find the rotation angle, okay? Because you will not know that just by looking at the equation. And then another remarkable fact is that the discriminant, the B squared minus 4AC, is invariant under rotation. Again, that's just another long calculation that basically says that B prime squared minus 4A prime C prime is actually the original discriminant. Now that looks like a lot of stuff, but it's simple algebra, it's simple trigonometry, and just a lot of busy work. I do this in my honors section, obviously, it's complicated, but the results are simple. So when you look at this and you think, well, how can we use this to solve a simple problem? Oh, I covered this up, here we go. Let's look at an example. Notice here, let's look at this particular conic, because in general, the conic will go ax squared bxy plus cy, and I'll go ahead and fill in the rest of these. But we don't really, it's not that we don't care about the others. The others don't really impact anything like the A, the B, and the C. So we get dx plus ey plus f equals 0. So this is the general conic, and in calculus 3, you'll extend this to the quadric surface. So this is what we call the general conic. The general conic. And so if we have something like this, notice here, we have xy plus 9. So we've got a b and we have an f, but everything else is 0. So now we just write this down. It's like, okay, well, the theory says, Professor Ron says the theory gives us this as the angle. So we have a is 0, b is 1, and c is 0. So now when we fill this in, we get theta is 1/2 the inverse cotangent. Of course, that's going to be 0. So what's the inverse cotangent of 0? Well, it's pi over 2. Again, we know the inverse cotangent lives between 0 and pi, and 1/2 of that is pi over 4. So the rotation angle here is pi over 4. Okay, so let's go to our rotation equations and figure out what this will look like in the translated system. Again, when I drew it down here, it was kind of wonky, and I said, forget this. And then I did a nicer drawing over here. Now, notice here, this is our x and y equation. So we just substitute the value of theta. Let me drop my, what did I do with my initial? Again, I've covered it up. I want to show you the formulas that we derived. I covered it up somewhere. Here we go. Oh, right in front of me. Notice here, we've got these formulas here, and we got this one. So when I do these, ladies and gentlemen, I'm using these formulas. So we substitute to get x and y in terms of the new system. Again, the prime, the cosine of pi over 4 is 1 over root 2, so we get x prime over root 2, minus, again, sine pi over 4, y prime over root 2 with the minus sign. And now for the y, we do the same thing, filling in the value of theta and getting this. Then I've written here, we substitute. So when you substitute here, notice we've got all these 1 over root 2's here. So we just say x times y, and factor the 1 over root 2 twice to give us 1/2. And then of course, this is just a difference of 2 squares. And we get 1/2 x prime squared minus 1/2 y prime squared, and take the 9 over. And then of course, divide by -9 and flip everything around. And we're seeing that our actual rotated conic is a hyperbola, where the foci are on the vertical axis. Now, notice here, this is what we call a conjugate hyperbola, because the a and the b are equal. The a squared and the b squared are equal. So now we're thinking, okay, well, how do we do this? Well, c squared is a squared plus b squared, so that's 36. So c is equal to 6. So the foci are on the vertical axis, so this will be 0 plus or minus 6. And then, of course, the square root of 18 will be 3 root 2. So the vertices are 0 plus or minus 3 root 2. Now, of course, if a squared and b squared are equal, then b over a, or a over b, again, 1. So we get y prime is equal to plus or minus a over b x prime. So these are the asymptotes. But notice, these are just the axes of the new system. So when you rotate pi over 4, if I turn this around this way like this, you see that the actual asymptotes are just the old axes. So this is why they call it the conjugate hyperbola. So now when you rotate, you've got your center here, and then you've got your foci out here and your vertices here that we computed. Now you're thinking, how can we get the old, so to speak? For instance, how could we write these in terms of the x and y? Well, we can just go ahead and utilize these equations here. And notice when you substitute, this value right here is actually -3, 3, and this value here is 3, -3. So we can toggle between the new rotated vertices in the old. So again, the V2 prime is 0, 3, root 2. The V2 in the old system is negative 3, 3. The V1 prime is 0, negative 3, root 2. And the V1 in the old system is 3, negative 3. So this is what I was talking about when you compare the two methods, so to speak. When it comes to rotation, there's a lot more complication because again, you necessarily introduce trigonometry. So again, when you want to use your translation equations, you want to go from B prime into D, the X and Y, so you can just use these and make the substitutions. So the idea is when you multiply here, the Y prime, that's the 3 root 2, that absorbs the 2 and also will give you the 3 that you're looking for. And of course, in the first case, notice here, when we get the 3 and the negative 3, it's the same thing going on. The idea is that when we work with translation equations, it's a simpler construct, but it's analogous to the rotation. So one thing that if this is remotely interesting to you, I would say once you have a little bit of time, research this. You can look at this on Wikipedia, or you can look in your ebook and look at some of the theory here. This is a really fun thing to do. Again, I'm not even sure how I'm going to be able to fit it into my next class, but I'm going to try to squeeze it in so it's not just kind of like a cultural exercise on the last day of class. But the main thing is this: after you finish studying your test, go back and do this calculation that we've done here and convince yourself of the rotation equations, and then go back to this example and rework it and see basically that when it comes to rotation, the XY term is the rotation term, and it will reveal the actual rotation angle theta. So when you do that, this is what we derive. When we zero out that B prime coefficient, that equation specifies that theta must be this. So every time you have a rotated equation, you look for A, B, and C. You use those to solve for the angle theta. Once you have the angle theta, then you can use your rotation equations to replace the x's and the y's in your given equation with the new prime equations. Substitute, and then you end up with a primed equation, which is the new x prime y prime system, which is what we have here. So again, it's like doing the translation, but just slightly a little bit more complicated. So what I wanted to try to do is just kind of give you an introduction to this. And again, when you take your linear algebra class, you will actually approach this through linear transformations and focus on orthogonal matrices, which again, you can write all this in terms of matrices. So there's so much theory going on here, and it's a lot of fun. So I thought I would just like take the opportunity at the last day of class just to share that with you. And of course, if you get bored when you're studying and you just want to work through this, be my guest. You can see again that we just employ the basic identities that we have learned in the trigonometry portion. So what I would recommend is, like I said before, I know I sound like a broken record. Make sure that you take the time to go through your new material. Go ahead and knock out your WebAssign. Get that done this evening because it's due by 11 p.m. And then do a spot review on any ideas that we covered with the review questions. That is, I'm not so good on the transformations. I need to review that, or I need to go back and review some log equations, or I need to check some domain questions or things like that. So go ahead and make a point to set up a schedule when you take your test. That is, go ahead and organize everything you have. You got this nice long window to take this test, and be sure to do correct submissions, and also be sure that when you are done with your test, that you do your scans and you upload your scan to Blackboard. You must have successful transmissions of your submissions of your WebAssign work, and you must have a successful submission for your test work to get credit. And I have prepared you for this. So finish the class strong, follow the directions, know that you are now on a good level to conquer the calculus. The calculus will keep you very busy. Calculus is one of those studies that is actually quite profound. It's like reading great literature. The applications of the calculus are infinite, and that's no pun intended. So make sure that you take the time to finish strong. If you need to take a good nap and relax, do that. Utilize the time that I provided for this. And then once you're done with your test and your other testing, you can now prop up your feet and enjoy the fruits of your labor. Now, I will be holding office hours today and tomorrow, and I will send out the email messages for that. If you would like to stop by, if you have any questions, I'll be glad to help you with that. And so stay warm, at least while it's cold, and good luck with your studies. And if I see you at office hours, fine. If not, do a great job on your test and have a safe break, okay? Bye, everyone.
Someone asked how many questions will be on the final.
Oh, 50,000.
There you go.
I would say anywhere between 20, 25.
Thank you, sir. Have a good evening.
You all don't need to worry about the number of questions. If you understand the material, then you're fine. Don't worry about that, and I've given you plenty of time to take it. Thank you.